Hello, this is KiboCUBE Academy, Lecture 25, Introduction to CubeSat Onboard Software and Simulation Environment. So first, let me introduce myself. I'm Satoshi Kari, an Associate Professor of Department of Aeronautics and Astronautics, the University of Tokyo. I had several experience to develop micro and nano satellite mentioned in this slide, the Prokion, Aquarius, Sophia I1, and also I developed some AOCS module. And my research topics include micro nanosatellites, astrodynamics, formation flying, global navigation satellite system, attitude determination and control, and numerical simulation. So today, I'll talk about the softwares for satellite development, and this slide shows the contents of my lecture. So let me start from the introduction to software for satellite development. So in space development activities, software plays a crucial role. And there are so many software used in satellite development: CAD, structure and thermal analysis, electrical power analysis software, and astrodynamic simulators. They are used in mission analysis and satellite design phase. And there are also flight software, ground station software, telemetry data analysis software, mission data analysis software. And they are used in development, test, and on-orbit operation phase. In particular, the flight software is most important for the success of satellite projects. So there is a very interesting paper, Fatal Software Failures in Spaceflight. And according to this paper, the software is responsible for 3 to 33% of failures, and with most value close to 10%. And there are several examples of software failures in space project. In the case of Viking 1, so due to an error in the reprogramming of the software controlling the battery's charging cycle, the configuration of the antenna alignment was overwritten, and the mission was ended by losing the communications. And in the case of the Astro 8 satellite, it's a Japanese satellite. Because of the software error, the satellite started to spin up and very rapidly, and some parts, like solar panels, are tore off. So this kind of the very big failures are caused because of the software failures. And many micro nano satellites also have software failures leading to mission failures. So to avoid these kind of failures, the software testing is essential, but often gets neglected in spacecraft development because spaceflight technology is historically and also traditionally located in the area of mechanical engineering. This means that software engineering is seen as a small visually discipline. Satellites, but one good point of this softwares, the satellites are largely non-repairable, but software is typically the only element that is repairable. So we can upload it, we can upload tuned parameters, debugged software, and new applications to change or fix the satellite behavior. So software in satellite development is very, very important, and we need to learn how to create the very good, reliable software. And to develop a reliable flight software, we need reliable numerical simulator for testing the flight software. And also to correctly operate the flight software, we need a reliable ground operation software. So I believe the combination of these three software, flight software, numerical simulator, and ground station software is very, very important. So this lecture focuses on flight software, numerical simulator, and ground station software. And we will learn the purpose and the overview of this software. And this lecture also covers software management. We will learn how to develop reliable software with a team. And finally, we examine an example of software suite for satellite research and development. We will learn about open source software developed by the University of Tokyo. So next, I'll talk about the flight software. So firstly, I'll introduce the purpose of flight software. The flight software is responsible to achieve the required functions of the satellite with the available computer resources. And there is a list of typical roles of flight software. The first one is telemetry generation and command execution for communication with ground stations. And second is storing telemetry and mission data into onboard memory. And also we need to store the scheduled command. And the third one is the periodical processing of implemented applications to collecting sensor data or application of the attitude control system. And execution of autonomous application to maintain a healthy satellite bus system and to operate the mission payload is also important. And when we implement this kind of the flight softwares, we need to carefully consider the constraints of, coming from the hardware. For example, the computer power and memory is very limited because of the limitation coming from CubeSats. And of course, we need to consider the radiation effect to select the CPUs. And yeah, because of the radiation effect, the computer power and memory is also limited. So this table shows the example of computer resources for CubeSats. And usually the memory size or computer calculation power is very, very limited compared with the normal laptop computer or the computers used in the robot working on the ground. So next, I'll talk about the basic features of the flight software. The first basic feature is command. The command is the data sent from a ground station to a satellite to control the satellite behavior. So there are two types of commands. The first one is real-time command. It's a command executed soon after the satellite receives it. And the second one is scheduled command, a command to be executed at the specified time. And using these two types of command, we can freely and flexibly operate the satellite. So to handling the scheduled command, the scheduling execution timing of command is an essential feature of the flight software. And when we consider about the command, we also need to care about the safety and security of the command. Of course, we need to ignore the commands for other satellites or commands from unexpected operators. And of course, satellites should ignore the commands with invalid parameters to protect the satellite. So next basic feature is telemetry. The telemetry is data sent from a satellite to ground stations. And there are three types of telemetry. The first one is for housekeeping data, HK. The HK is basic status information of satellite components to monitor the health of the satellite. And HK is usually periodically and continuously sent to ground stations during the contact with the station. The second one is stored data. The stored data is information stored in the satellite onboard memory, and when the satellite does not communicate with the ground station. And the third one is the similar with the stored data, it's mission data. It's the data acquired from the mission instrument, such as a telescope. So in the case of the telescope, the mission data will be the image data. And these stored data and mission data should be downlinked to the ground station when the contact with the ground station. And scheduling downlink timing of telemetry data is an essential feature of the flight software. And similar with the command, the encryption is required if you want to keep your data secret. So these basic features, the command and telemetry is very, very important for the flight software. And in these days, the security, safety, and encryption is also important to consider about the command and telemetry. So next, I'll talk about the advanced applications. So for the autonomous operation of the satellite, this kind of the advanced application is very important. So I'll show you the example of the attitude control algorithms. So this figure shows the block diagram of attitude control. This green one is the sensor data or the actuators to control the satellite attitude. And this orange block shows the states or the data value to such as estimated angular momentum or estimated angular rate or something. And the blue one is the block of the each algorithm to determine the attitude or to generate the to calculate the control torque or something. So this blue blocks is the means the applications implemented onto the flight as the flight software. And in the attitude control system, firstly, we need to correct the sensor data. So the first one is the sensor data handling. And to get the sensor data, of course, we need to set the sensor configurations. And after that, we can get the the observation data from the sensors. And to remove the noise on the observation data, of course, we need to implement the filter algorithm. And after the filtering of the observation data, we need to estimate some states like the angular rate or quaternions, and using the Kalman filters or other attitude determination algorithms. And we also need the calculation of target attitude to point some position on the surface or something. And by using the estimated attitude and the target attitude, we can calculate the control torque to stabilize the attitude using the PID controller or other controllers. And to generate the required torque to control the satellite attitude, we need to make some command to the actuators and set actuator configurations. And of course, we can get some information from the actuators, like the control speed of reaction wheels. And these applications are implemented as a flight software, and flight software operating system uh, manages these applications. And other important features of the flight software for the satellite is on-orbit reprogramming. As I said before, the satellites are largely non-repairable, but software is typically the only element that is repairable. So to keep the repairability of software, on-orbit reprogramming feature is essential. So there are several types of reprogramming. The full reprogramming means the rewrite all programming memory, and partial reprogramming means rewrite partial region of program memory. And of course, the full programming is more flexible, but high risk to do that. And partial reprogramming is more low risk and low flexibility. So we need to carefully consider the risk of reprogramming and select which types of reprogramming we should use. So that we need amount of time for the uplink of the new program data, and of course we need to care about the data loss during the uplink. And if data loss is happened, we need to uplink again the lost data. And of course, we need to carefully consider about the failure due to the bugs in the new software. So we need to keep the old software after the new software is working well. And of course, to avoid some big failure during the reprogramming, we need to store the critical areas to be maintained and not related. So, yeah, but as again, of course, the reprogramming has some risks, but it's very, very important for the satellite operation because the software is typically the only element that is repairable. So finally, I'll talk about the limitation from the hardware. So especially for the CubeSat, we need to use the limited computer power and memories. And of course, we need to consider the radiation effect. And the reset or reboot of CPU is essential for the CubeSat operation. So usually we use the watchdog timers or mutual monitoring system to detect the hang up of CPUs. So making this kind of the software is also important. And also we need to consider about the programming language is also limited. So traditionally, for the embedded software system, we need to use the C or C++. And recently, Python and Rust are started to use. So yeah, you can consider to use this kind of the programming languages. So next, I'll talk about the numerical simulator. So this slide shows the purpose of a numerical simulator. So we can use the numerical simulator as a mission design and analysis. So we can calculate the orbit and attitude to for the mission analysis, and we can analyze the power balance or thermal analysis or communication visibility analysis, and lifetime and deorbit time analysis. And as I mentioned before, that we can use the numerical simulator to verify the flight software. So to verify the onboard autonomous functions, attitude determination and control algorithm, and orbit control algorithm is very important. So we need the good numerical simulator to test the flight software. And also we can use the numerical simulator for the operation training or the operation command validation before before we send the command to the real satellite. We can validate that the command is working well on the numerical simulator. And to construct the numerical simulator, first we need to simulate the space environment. Then the understanding the space environment is essential for the thermal power balance, communication, visibility analysis. And of course, it's important to calculate the orbit disturbances or calculate the sensor observation data, like the sun sensors, sun direction, or magnet sensors, magnet field information. And the space environment includes the position of planets or rotation of planets. And it also includes the position of stars. And the geomagnetic field or atmosphere air density information is also important to calculate as a space environment. And to the satellite power balance analysis or the sensor data calculation, the eclipse calculation is also important. And I also want to add the artificial infrastructure as a space environment. So the position of GNSS satellites or position of data relay satellites are very important to the realistic satellite operation. So I want to add this kind of the artificial environment as a space environment to simulate the numerical simulator. And the second important feature of the numerical simulator is the satellite dynamics simulation. So satellite dynamic simulations are essential for the satellite position and attitude calculation. And to calculate the satellite position and attitude, we also need to calculate the disturbances acting on the satellite on orbit. The disturbances includes the high-order geopotential, third body gravity effect, or magnetic disturbances, torque, or solar radiation pressure acceleration and torque, and air drag acceleration or air drag torque. And by using this kind of the disturbances information, we can calculate or propagate the satellite orbit or attitude. And to calculate the satellite orbit, we have two approaches. The first one is analytical calculation. It's the kind of the Kepler equation, or we can use the SGP4 with the two line elements. And the numerical integration, usually we use the longitudinal method to propagate the satellite orbit. And the satellite attitude propagation, we also use the longitudinal method. Of course, together with the disturbances effect. And third important role of numerical simulator is satellite components emulation. So the satellite components emulation is essential for the realistic test for satellite attitude determination and control algorithm or satellite orbit control analysis. And the satellite components emulation includes the emulation of the electrical power. It means the switch state of components or power consumption of components. Yeah, when we consider the power consumption of components, of course, we can use this kind of data for the power budget analysis. And the emulation of thermal information is also important. We need to emulate the heat generation coming from the components, or we should consider the thermal conductance between the components and mounted surface of satellite. And also the emulation of communication between the components and onboard computer is very important. We need to emulate the telemetry and command of the component. And other important things is the noise on the sensing data or noise on actuation torque or mounting position and coordinate of the components. Or also we need the failure emulation of the components to analyze the failure case, FDIR case analysis. So this figure shows example of the gyro sensor output. So this smooth line, this orange and yellow and purple line is the true angular velocity, and this red and green and blue line is the measured data of the gyro sensor. So you can see some noises or some bias offset or to emulate such kind of effect of the realistic gyro sensor. And this figure is example of reaction we use. And the bottom one is the ordered torque, and this one is the actually generated torque. And you can see some time delay between the ordered torque and the actually generated torque. So this kind of the realistic emulation of the components can help the realistic test of the satellite attitude determination and control, or of course the power budget analysis or thermal analysis using this kind of the numerical simulator. So to construct the numerical simulator, this space environment simulation, satellite dynamic simulation, and satellite components emulation are very important. So next topic is ground operation software. So this slide shows the purpose of ground operation software. The first one is operation planning. So we need to determine the aus and loss time. It's the acquisition of signal and loss of signal time with satellite orbit information. And we also need orbit determination for future operation planning. And sometimes the orbit determination is determined by other persons. But basically we need such kind of the feature. And the second one is the ground station antenna direction control. So we need to calculate elevation and azimuth from satellite orbit to direct the satellite position and generate some signal to control the antenna direction. The third one is telemetry quick look with GUI, the graphical user interface. So we need to display the real-time telemetry in good GUI to quickly check the satellite status. And of course, we need the command sending system that's to send the command to satellite. And we need the data storage system that store telemetry and command data in the database. And the final one is the telemetry analysis. So we need to analyze the telemetry data to get mission data or to check the health monitoring of the satellite. So these kind of the features are needed for the ground operation software. So from next slide, I will talk about the detail of each topic. The first one is the on-ground antenna and driving software. The purpose of this software is the control the antenna direction. It means the elevation and the azimuth to point the satellite direction. And the normal sequence of this software is are written in here. First, we need to get the satellite orbit information. For example, we can use the to-run element TLE from the spacewalk website, and calculate the satellite position in ECEF frame. It's the Earth-centered Earth-fixed frame. And calculate the antenna position, target direction. It's the elevation and the azimuth. And finally, we need to control the motors on the ground station antenna. So next software is front-end software. It's the command and telemetry handling GUI. So the GUI, the graphical user interface, is very important to improve operational efficiency and reduce the frequency of operational errors. So we need the command handling GUI and the telemetry quick look GUI. And for the command handling GUI, usually we use a list of sending command like this image. And it's very important to have some file input system for the scheduled planned command list. And of course, in the satellite operation, sometimes some emergency case is happened. So to cover such kind of the emergency case, we need the special command selection interface for the emergency operation. And for the telemetry quick look GUI, we need a list of received telemetry data and its value. So, and this bottom figure shows the example of not at the telemetry GUI. And the time history graph was state indication with colors, and other graphs are effective to quickly understand the satellite status. And the next slide, you can see the example of telemetry quick look GUI with Grafana. And here you can see the time history of battery, heater current, or switch status of each heaters, or the temperature of each component, and the time history of temperatures. So this kind of good looking the GUI is needed for the effective operation. So next, I'll talk about the backend software. It's the data delivery system and data storage servers. So the received telemetry data is the most important artifact of the satellite mission, the satellite operation, and must be kept in strict confidence. So the telemetry data, including housekeeping data and stored data and mission data, should be stored in the on-ground storage servers. And the transmitted command information should also be stored on the server to verify what kind of satellite operations were performed. So this this is the example of database server connection. And yeah, the telemetry data is coming from satellite should be stored in the database servers. And yeah, the command data is also stored database servers. And finally, I'll talk about the advanced application. It's the automatic operation. So when operating a large number of CubeSats simultaneously, it is essential to automate the operation. So example of automatic operation I show you. This is the case of the automatic command generation before the operation pass. So in this case, the target imaging point is selected by users like this. And the target attitude of the satellite to get the image is calculated and maneuver plan is generated automatically. And the command list to realize the maneuver and imaging is generated like this. That was we changing attitude to the target point and power on camera and take image and change attitude to the sun pointing or to get the solar power generation. And this command list is validated with the numerical simulator by checking the power generation or thermal analysis or attitude angular velocity upper limit or something. And when the command list is feasible, it is checked by the simulator. The commands sent to the satellite in the next uplink pass. So this kind of the automatic operations are also important in these days. And in this automatic operation, the grants operation software and also the numerical simulator is very, very important. So next topic is software management. So first we are talk about the purpose of software management. So the purpose of software management is to develop reliable software and reusable software. And it is also important for the cooperative development with team members. And to realize the above requirements, and the following features are important. The readability of code and modularity of codes. And we need to decide some coding rules in the team members. And the peer review between team members are very, very important. And finally, the test is very important. We need to do test, and a lot of tests to keep the quality of software. And first, we are talk about the coding rules. So coding rules includes the naming rule and the coding format. And the naming rule means how to decide the file name, variable name, and function names. And we also need to care about the abbreviation rule. So the naming rule, in the naming rule, we need to define which types of the character cases to use, the snake case or upper snake case or kebab case or Pascal case or something. And for the abbreviation rule, where for example, we can use the Q as a quaternion, but of course, sometimes it's very difficult to understand what the Q means. So sometimes we can define the abbreviation rules. We should use quaternion, not the single letter Q. So this kind of the naming rule, defining the naming rule is very, very important for the readable code development. And coding format is also important. And the coding format includes the indent style or length of a line or something. For example, yeah, you can choose the Auerman styles or K&R styles. Yeah, of course, it's depending on the software developer, but we need to define some rules for the team development for that software. And for the coding rule, I strongly recommend to use the formatter. The formatter means the automatically correct the for code formatting to suit with the defined coding format rule. And to define the coding rules, yeah, we can refer to some popular coding rules like the Google C++ style guide or WebKit code style guidelines or Google Python style guide. And yeah, of course, we can refer these kind of coding rules with the small originality for each team. So anyway, to decide or to define these kind of the coding rules before starting the development of the software is very, very important. And next topic is the interface management for the modularity of software. That define the interface between functions is very important, and to clarify the division of work, and it can achieve the modularity of the source codes, and it is it helps team development. And we need to define the input and output of functions. And the input is the meaning of arguments and the meaning of returns. And range of arguments and returns are also important. Yeah, because we need to return error when the value overs the range. And also the definition of dimension, unit, and frame is very, very important. So in the space sector, yeah, we use a lot of unit or the frame definition. Yeah, for example, is the angle in unit radian or degree, or is the sum vector in the ECI frame or the body fixed frame. Yeah, such kind of the miscommunication should be happened if you don't define the concrete input and output of function, the definition of input and output. So that this kind of the interface management is very important to develop software. And the third one is the version management. So software is easy to edit. So the software version control is very essential to track who made what changes and when. So for effective collaboration and ensuring the stability and consistency of code across development stage. And for the version management system, we can use Git or GitHub. So Git is a distributed version control system that enables efficient tracking of changes. And GitHub is a cloud-based platform that uses Git for hosting, managing, and collaborating on repositories. And GitHub also has the additional features like issue tracking or pull requests and GitHub Actions. And to use these kind of the features, we can effectively develop the softwares. And this is the example of the repository management of using Git. And here is the master branch. we have other development branch here, and we have some bug fixing branches, or the release branches, or feature development branches. And yeah, by using the Git, we can easily making this kind of branch, and we can easily track the change history of each branch, and also the merge history of the main branch, or master or development branch. And this kind of the version management is very, very easy, very, very important for the software development. Yeah, and also the peer review is very important to keep the quality of software. The source code should be reviewed by other team members before merging to the main branch, and to ensure the quality and identify bugs and improve the maintainability. And yeah, GitHub has peer review system as a pull request, and yeah, we can use the pull request at yeah, for the peer review system. And yeah, also the GitHub has the GitHub action. It's the automatic bots, and using the GitHub actions, we can check the code format or run format before merging, or we can check the yeah, that software is buildable, or yeah, unit test is passed, or the output test is good, or something. So using this kind of the automatic bot system, we can yeah effectively develop the satellite software. Yeah, and yeah, the reviewed by team members are very, very important, because the checking the code is readable or naming is readable. So it's very important to for the readability or reusability of that software for the not only the current project, but also the next future project. Yeah, and yeah, the team members should carefully check for the potential bugs, or the developer should add test result to clarify the adding source code is correct. So this kind of the peer review process, yeah, can improve the quality of software, the quality of source codes. And finally, I will talk about the software testing. So it's very important thing is that the what had not been tested does not work well. And so we should test the all softwares for the software development. And there are two types of the test. The first one is a unit test, and second one is integration test. The unit test is the verification of the functionality of individual components or modules in isolation to ensure they work as intended. And any code, no matter how small, should be tested. So, and the unit test can be automatically done when someone makes a pull request, using the GitHub actions. So this figure shows the example of unit test. And yeah, there are 6 tests for this epoch time class in the numerical simulator. And yeah, time constructors are tested here, and the time calculation, the adding or subtract is tested here. And yeah, there are also another test for the GPS time class. Yeah, and in this unit test case, there are over 100 tests, and in the every pull request, this unit test is automatically run, executed by the GitHub actions. This kind of the continuous testing development is very, very important. And for the integration test, this test is the verification of the interactions between integrated modules or components to ensure they work together as expected. So in the unit test, each functions or each modules are individually tested, but in the integration test, all modules or functions are tested together. And it is necessary to consider what kind of testing needs to be done on a project by project basis. So the integration test, the definition of integration test is very, very difficult. But in your project, you should carefully discuss with your team members what kind of integration test you done before the pull request or before the merging you are changing for your software. So the final topic is examples of software suite for satellite research and development. So I will introduce you the open source software project of ISSL. It's the Intelligent Space Systems Laboratory at the University of Tokyo. Our laboratory has released the OSS suite for satellite research and development. And you can see the old source codes from this link to the GitHub. So please visit the GitHub. So this OSS suite includes the C2A. It's the flight software, C2A here. It's a highly flexible flight software architecture. And S2V, it's the highly high fidelity astrodynamics numerical simulator here. And WINGS, it's a web-based ground station software. And the S2E, C2A, and WINGS can be executed independently, yet they seamlessly connect to enhance the spacecraft mission analysis and operational experiences. So you can see the connection between each open source software here. And from here, I'll talk about the overview of each software. So first one is flight software C2A. The C2A means the command-centric architecture. So our laboratory has been developed the C2A since 2013. And C2A has been developed with a focus on providing high reusability and high flexibility on orbit reconfiguration capability. So a major feature of C2A is its ability to describe the behavior of the satellite by command. And this software architecture has enabled the short-term development of the software and on-orbit reconfiguration to modify the functionality of the satellite. And in our laboratory, we already used this C2A for several micro nano satellites missions we developed. And most of the satellites were already launched and operated on orbit. For example, the Hodoyoshi 3 it's the 50 kilogram class microsatellite, and Procyon is the 50 kilogram deep space probe, and Aquarius it's the 6U lunar CubeSat, and Sophia I1 and OnlineSat is the 6U remote sensing Earth orbiting satellite. Today, I don't have enough time to talk about the detail of C2A, but you can access the detail of the C2A here. our GitHub repository. So please visit this website and yeah, to see the C2A core and to start to use the C2A or to join the development of the C2A. And yeah, C2A has this core code. It's kind of a library of C2A. And we also have this C2A AOBC. It's a user side repository. And yeah, the C2A AOBC means the C2A for attitude control onboard computer. And you can see some example of the attitude control algorithm using the C2A architecture. Okay. And yeah, this is the overview of C2A. And you can see the several hardware depending code here. And yeah, this red one is a C2A core code, and it's included in this repository. And this blue one is the user application or user defined libraries. And yeah, you can find the user defined application or libraries for attitude control system in the repository of C2A AOBC. And next one is the numerical simulator S2E. S2E means the spacecraft simulation environment. And our laboratory, ISSL, has been developing the S2E since 2016. And I am actually the main contributor of the S2E. And the S2E has the following features to realize high-fidelity astrodynamic simulations. For the space environment, the S2E has simulate the celestial body position information using the NASA's SPICE library and rotation of the Earth and the Moon. And yeah, we can calculate the geomagnetic field with the IGRF and air density calculation with the NRLM size 00 model. And yeah, GNSS satellite position is emulated, and of course, we can calculate the eclipse by the Earth for the satellite. And the satellite dynamics simulation, we have the attitude dynamics propagator using the longitudinal method. And yeah, we can also have the predefined attitude mode for the easy orbit behavior analysis or something. And for the orbit propagation or orbit calculation, we of course have the Kepler motion without any disturbances. It's the most simplest orbit calculation. And orbit propagation with the longitudinal method with the many disturbance on orbit disturbances, or of course we can include some orbit control using the thrusters. And of course we have the SGP4 orbit propagation with the two-line element. And yeah, you can see the example of the SC output. It's the example of the formation flank satellite analysis. Yeah, you can see the 3 satellites are flying together, making some special formation. Yeah, and for the accurate satellite dynamics calculation, we have the high fidelity disturbance models. Geopotential is up to 360 degrees, and third body gravities, air drag force and torque with the multi-surface model, and solar radiation pressure force and torque also with the multi-surface model, and magnetic disturbance torque, gravity gradient torque, and also we have the micro vibration disturbances coming from the onboard reaction wheels. And flexible structure vibration is also implemented. We finished the implementation of such kind of the effect. Yeah, and the S3 has the many component emulation features. Yeah, position and coordinate definition of components, and noise and delay of measurement or control signals, and the telemetry communication and emulation of each component, and power switch control something. And yeah, S3 also has a thermal analysis feature or Monte Carlo simulation feature or multiple satellite simulation features. And yeah, it S3 can communicate with PC's comport for the health testing. Health means the hardware in the loop simulation. Yeah, so yeah, the S3 has a lot of features to help the satellite development and satellite research for the future satellite project. So yeah, and also you can see the all source codes in our GitHub workspace. So please visit our GitHub. And the final one is the ground operation software Wings. The we have been developing the Wings since 2020. And the Wings has been developed for use in satellite operations and ground tests and component tests. And the front end and the back end of Wings are implemented separately, and the front end calls REST API to connect the back end. Therefore, the user interface can be extended to be more user-friendly by modifying only the front end. So furthermore, by calling the APIs via script such as Python, it is easy to perform automated testing of components and build an automated operating system. So using the Wings, we can this is example of the GUI of Wings, and of course, we can use this kind of the GUI, but in the same time, we can use the APIs for the automatic operation. So the yeah. In our OSS suite, it is very important to combine these three software uh, for the to suit with your purpose of your research or your development phase. And the our OSS suite widely covers many satellite research and development activities from education to real satellite operations. Yeah, so in this table shows the how can you use our OSS suite for each situations or activities for the research educations to the satellite operations. And and this figure shows the Shields mode, the software in the loop simulation mode, and Shields mode, the hardware in the loop simulation for the satellite developing. And in the Shields mode, the C2A plus S3, you can use the C2A plus S2E, and it's the simplest testing configuration without control from outside. So you can test the automatic onboard algorithm like attitude control. And C2A plus S2 and Wings mode, this mode, the users can uplink commands to the flight software C2A and downlink telemetry from the software. So in this case, you can emulate the actual operation, including the flight software. So it's the kind of you can use the verification of the operation. And in the Hills case, you can use the real onboard computer as hardware here. So C2A and Wings naturally work with hardware like OBC and ground station equipment. It's the real one. And the SE can also work with hardware by connecting it to the PC USB ports, and users can make a health system like this. So in this health system, you can test your real or onboard computer hardware is feasible for the from the viewpoint of the computational power, computational cost, or memory usage or something. So by using this ISSL OSS suite, you can you can use from the research education and the satellite mission design and the satellite development, satellite verification, and satellite operation. So this kind of the how can I say, satellite research and development software is very, very important for the effective space activities. And I'll show you the example of usage of this ISSL OSS suite in the satellite development. So we have developed one year size AOCS module. This is the photo of that module, and that includes the full feature of 3-axis attitude control. So it means this module has the star trackers, gyro sensors, and sun sensors, magnet sensors, and magnet talkers, and reaction wheels, and GPS receivers. And to test the flight software of this AOCS module, we effectively use the OSS suite during the development of this module. And the customized S3 AOBC and C2A AOBC for the AOCS modules are developed, and these two softwares are also published as OSS in GitHub. And the flight software C2A AOBC was verified with the shields and hills configuration. And this is the one example of the attitude control with the magnet talker. You can see the error of the sun angle leads to the less than 10 degrees. You're only using the magnet talker, not using the reaction wheels. Okay, this kind of the how can I say, usage of S3 and C3 and also wings is very, very effective for the satellite development. So finally, I conclude my lecture. So the software used in satellite development was introduced, and the importance of software development to improve the success rate of satellite was explained. And the objectives and overview of flight software, numerical simulation, and ground station software were discussed. And key features of each software were explained. And an overview of software management methods were introduced. The software management method is essential to realize reliable software development with team members, and it is directly connected with the success rate of satellite. And finally, as example of flight software, numerical simulation, and ground station software, the ISSL OSS, the open source software suite, was introduced. The details of the independent software was explained, and the connection between the software was also introduced. So that's all in my lecture, and I hope you can learn the importance of the software development in the space activities. And if you have any interest to our OSS activities, please visit our GitHub repository and please join our OSS activity. And if you have any questions, please feel free to contact me with GitHub or something. Thank you very much for your kind attention, and thank you.